Hey guys, welcome to Brogrammers. So in this question, we will solve 7th August Leetcode problem of the day. And the question says we have to convert this number into its English word representation. What does this mean? What does this mean? For example, you have this example. Okay, we'll take 111, 256, 789. Then it is 100, 100, 1,000,000, 256,789. Okay, so this is our task. This we have to achieve from this number. Okay, so this question it's bit tricky, right? It's a bit tricky. Why I'm saying this? Because you need some mathematics and you need recursion in this, because each and every time you have to take this word, check whether it is the 100 position, 10th position, or 1's position. Each and every time you have to check. So for checking again and again, we use recursion. Okay, so we'll understand this question in much deeper manner. Okay, I'll drop this first, right? Okay, we'll take it 9 and this is 2000. Okay, so the simple logic is, as we all know from our childhood, then that if we have if we have this three words, we'll divide this whole number into three parts. Okay, this is part 0, this is part 1, this is part 2. We call this as ones, this is 1000, this is million, and if we have something more, then it is billion. Oops, sorry, my bad. Then it is billion. Okay, in this example we don't have this million word, so I will drop it for now. Okay, this is just for the explanation. I took this. Okay, so we need some function, or somewhere we need to store that. Okay, if we are in 0th index, means we are in 1's position. If we are in first index, means we are in 1000 position. If we are in second index, means we are in million, and if we are in third index, means it is billion position. Okay, for this we have to store this concept somewhere. Okay, so I took this function. Its name is TMB. TMB means 1000, million, and billion. TMB. Okay, so if you are in 0th index, means you are in 1's position. If you are in, I'll index it 0, 1, 2, 3. If you are in 0th index, means you are in 1's position. If you are in 1000th index, means if you are in first index, means it is in you are in 1000th position. If it is in second index, means you are in millions position. If you are in third index, means you are in billion position. Okay, this is a simple intuition that we have to think. Okay, somewhere we have to store it. So one thought process is very clear, that I have divided this number into three categories according to ones, thousands, millions, and billions. This is sorted. Now you will tell me, okay, this is okay. Now if we take this subpart once, for example, 789. How you will divide this? I have some simple logic. Okay, again you divide this into three parts. This is one part. I'll change the pen for better representation. Sorry, this is first part, this is second part, and this third part. First, second, and third part. Okay, again we will check. Since we know from our childhood, this is 1's position, this is 10's position, and this is 100th position. Once I'll ask you one question. Okay, how you will represent this in English? How you will represent this in English word representation? You will tell. See, it is very simple, bro. It is 789. 789. This is a simple word representation of this number. So this 7, you have to store this 7 somewhere. As you all know, that 7 is less than 20. 7 is less than 20. So I think one thought process, that whatever number which is less than 20, I will store it somewhere. So that whenever I'll need this number which is less than 20, I will quickly get it. Okay. So I made one function named below 20. I'll zoom it for you guys. Okay. So I made this function named below 20. In this function, I have stored from null, basically from 0th index till 19th index, all the word representation of number starting from 0 till 19. Okay, so this is okay. This is clear that okay, we have stored this number somewhere in the function. So whenever we need only single letter, I can store it somewhere. And I can retrieve it whenever I need. Okay, so I need this 7. What I'll do is I'll call this function. Hey, whatever present in your 7th index, just return me that. So it will go in this function. It will check in the 7th index. We have this 7. So what it will do is it will return me 7. Okay. Now what is the condition? You need 100. This is 789. You need 100. So I can make some shortcut. What I can think is, if I'll add manually 100, you know in string, right? Addition, concatenation. Okay. So in string, let's suppose the string name is word. Okay. So in this word, if I'll store this, if I manually write this 100, okay, then it becomes 700. This is just some short trick. Okay. So 700 is sorted. So you will tell me, hey, just tell me one thing. This is 718. How you will get this only 7? Now the concept is mathematics. Concept of mathematics. Okay. If you divide this number by 100, if you divide 789 by 100, what is the answer? Yes, only 7. You will tell me it's not 7, it's 7.89. Bro, it is integer. Integer only stores number, not decimals. Okay. So we'll get only 7 by dividing it by 100. By dividing it by 100, we'll get only 7. 7 is okay. 7 will call this function below. We'll call this function below 20, and we will pass this 7th index. Whatever the answer will return, it is 7. We have manually added this 100 in this string. Okay, this much is sorted. We got this first part. We got this 100 part. Now you will tell me, okay, you did this 7 part. Now how you will go with this 89? You need some logic to get this 89. I'll tell you. Yes, you are right. 789. if you modulo this by 100, you will get the last digits. Yes, you know the concept of modulo, right? I'll not teach you how to solve modulo, otherwise video will go long. If you get this, if you want this 89, just simply modulate by 100, you will get 89. Okay, you will tell me, yes, I got 89. Now what you will do? What is the English word representation of this? It is 89, 89. Okay, so this is 10's position, this is 1's position. So I have to store somewhere, this 20, 30, 40, 50, 60, 70, 80, 90. I have to store somewhere, then only I'll get this 80. Okay, so what I'll do is, now you'll tell me, okay, this is 8, means you will get this 80 from this. So you'll ask me how to get this 89. Again, simple. If you divide this 89 by 10, you'll get 8. You'll get 8. So you will call this tens function. Hey, tens, get the element at your 8th index. Give me the element at 8th index. Give me the element at 8th index. What is the 8th index element? What is the 8th index element? Yes, it is 80. 0, 1, 2, 3, 4, 5, 6, 7, 8. It is 80. It will return me 80. It will return me 80. Okay, I will. Right. So I will concatenate this 80. I will concatenate this 80 right over here in this word. EIGHTY 80. Okay. Now you will tell me, okay, you have sorted this 80 part. Now you again need 9. Again need 9. Yes, you are right. So you got this 80. You got this 80. Now you'll tell me, hey, how you will get this 9? How will you get this 9? It's simple. Just divide this 89. Just take the modulus of this 89. You will by 10. You will get this 9. You get this 9. You'll tell me. You'll ask me, hey, how you will get this 9? It is simple 9. And you know that we are storing single element in our below 20. In our below 20. Yes, in our below 20. So again, you will call this below 20. Again, you will call this below 20. Hey, below 20. Just return me the element. Just return me the element with whose index is 9. So it will return me 9, and we will store this return in this word. This word will store, so 89. Right? And we will pass this word into our main word. So our main word becomes 789. 80. Oh, sorry, my handwritings are horrible. 789. Okay, so now we'll ask me, hey, you have solved this 789. You have solved the 789. The 789, it is at index 0, which is 1's position. So you don't need to use this TMB right now. There is no use of using TMB right now. But whenever you will move this index from 0 to 1, you have to append the index position of this TMB. You have to append the index position. So what we'll do is we will have some index variable I. Okay, initially it was 0. Whenever our first part will get over, it will increment it by 1. And we'll increment it by 1. And we'll use the same process that we have used for the 789 to this 256. But once we will return this word for 256, we will append this index position. We'll append this index position word. Okay. So if you return this 256, you have to append 1000 as well. You have to append 1000 as well. I'll do it for you. Okay. So again, I'll rub this whole part. Okay. So now we'll take just this 256. Okay. Again, this 256 means this is 1's position, this is 10's position, and this is 100 position. Okay. 256 divided by 100. 256 divided by 100 means this 2. This 2 is at 100 position. 2 is at 100 position. So if you convert this into word, then it will be 256. Okay. So you need just 2. You need just 2 for now, and you know that only 2 is stored in this below 20 function. So you will call this below 20 function. Hey, below 20. Just return me the element whose index is 0, 1, 2. This is 2. Okay. So we'll store this word somewhere. Okay. Word equals to, first the below 20 will return me 2. I told you earlier, we will manually write 100. Okay. So 200. Now what is the condition? We got this 2 means 200. Now it's time for 56. How you will get 256? How will you get 56 from this 256? Simple. This 256 modulo 100. You will get 56. Again, call some check function. Hey, you get this 256. You get this 56. So we have this 56 right now. Now again part it into again divide it into 2 parts. Okay. So first one is 50, and it is 10's position. And it is 1's position. And you know that if you get any element who is at 10's position, means you have already this function, 10's function. You will call this 10's function. Hey, 10's, see, return me the element which is at index 5. So 0, 1, 2, 3, 4, and 5. Yes, it is 50. We will append this 50 in our word. Okay. So our previous word was this. If you remember, our previous word was this. Word equals to 789. 789. This is our previous word. We are forming our new word for this 256. Okay. So we'll store it this word somewhere. Okay. 789. Now we'll check. Now we'll again move to this 56. You got this 56. You appended this 50. Again. You want the 6 now. How will you get the 6? Yes. 56 modulo 10. 56 modulo 10. You'll get 6. You need only 6. Which function will help me? Yes. Below 20 function will help me. So you will again call this below 20 function. Below 20. I'm writing it. I'm a bit lazy. Okay. I'm writing it in BT. BT means below 20. Okay. So you will call this function below 20. Hey, below 20. Return me the element with index 6. Which is that element? It is 6 only. Okay. Append this 6 in this word. Append this 6 in this word, again divided 6 divided by 10, which is less than 9, which is less than 0. Okay, so you got our next division word. You got our next division word. That is this 256. Okay, so now this word is clear, but you have to understand this. Now you are in first index. You are in first index means it is 1000. It is 1000. Okay, so to append this 1000 as well in your word. Okay, you have to append this 1000 in your word means 256,000. 256,000 and add this word right over here. Add this word right over here. This is word. What is this word that we have stored? 789. So our now new word becomes 256,789. Yes. So our two divisions are over till now. Our two divisions are over till now. What we'll do is increment this index to one pointer, that is from 1 to 2. So now our I will point to this 2. This 2. Now check this 2 in our TMB function. In our TMB function. Okay. What is there in our TMB function at index 2? 0, 1, 2. That is million. So whatever word we will return for this index, we will append million. We will append million. It will become 111 million. Okay, 111 million. So again, the same intuition that we have seen for this 256 and this 789. I will write it more here. 256, 789. This is 0, 1, 2. Okay, right. So we will again do the same thing. We'll again do the same thing. That hey, we'll take this 1, 1, 1. Again, this is 100. This is tens. This is ones. Simple. So you need this first element. You need this first element. Yes, I told you already. Divided by 100, you will get this 1. You need only 1. You need only 1. Which function will help me? Yes, below 20 function will help me. Okay. So again, make one new word. Again, make one new word. And append this below 20 return call. That is 1. That is 1. Because at first index, we have this 1. Okay. So our one case is over. One case is over. Now what to do? What do you need? What do you need now? You need 11. You need 11. Okay. How you will get 11 from 111? Yes. So now which word you need? You need 11. Just modulate by 10. You get 11. Now from this 11, check whether it is less than 20. Yes, it is less than 20. So before this, I forgot one thing. You have appended this one. What we are forgetting? We are forgetting to append 100 manually. Yes. So we'll write this 100 manually. 100. So now the part is now you need just this 11. Okay. You need this 11. You need this 11. How will get this 11? You'll right. So this 11 is below 20. This 11 is below 20. Below 20 means check this below 20 function. Check this below 20 function. What it will return? It will return. You'll ask, okay, hey, below 20. Just return me the element which is at index 11. Which is that element? Yes. It is our 11. It is our 11. So you will append it 11. Okay. This is my word. So 111. 11. Okay. So now what is the task? Simple. Append this word. Append this word right over here. Append this word right over here. Okay. So and one more thing. More thing. Before appending this word, yes, we are forgetting something. We are in second index. So what we have to append first? Yes, this million. Okay. So before appending this word, we will append million. So 111 million. Now append this word. Okay. So 111 million to it is 100. 256,000. And what this word has written? 789. 789. Yes. So this is how the recursion works. Okay. So I hope you got the dry run of this word, of this nums. We'll take one more example. For example, you have nums just 2000. Just 2000. If you notice something, this 2000 modulo, if you do 2000 modulo 1000, it is equals to 0. Yes. So you don't need to check any, you don't need to divide this into any parts. You don't need any division. Simply what you will do is you will divide this number by 1000. Divide by 1000. This is basically an edge case. Okay. So you will get this 2. You get this 2. And you know that this 2 is basically stored somewhere where, yes, it is stored in our below function. It is stored in our below 20 function, this 2. We will call this below function. Hey, below function, return me the element which is at index 2. Okay. That is nothing but 2. Okay. And increment the I. Increment equals 0. Now it's 1. Whenever you will encounter this first index, yes, you will go to this TMB function. What is stored in our first index? Yes, it is 1000. So what you will append? You will append 2 plus 1000. 2 plus 1000. Okay. Again divided by 1000. This number is less than 0. Break it. My bad. This spelling is wrong. THOUSAND. 2000. Okay. Yes, this is what we need. This is 2000. This is the English word representation of 2000. This is the edge case. Okay. Whichever number is divisible by 1000, we need not to divide it into any further parts. Just divide it by 1000. Check the index. At which index it is lying. Whichever index it is lying, just check that index in this TMB and append that number as well as its TMB element, and you will get your answer. This is a simple intuition for this question. Okay. So now we'll write a pseudocode. Right. So before writing pseudocode, we'll write a thought process. Right. So what is the thought process? First, right. So what is the first thought process? Yes, take the modulo because we need the last index. First. So take the modulo of nums. Okay, take the modulo of nums. So whenever you will do modulo of this number, okay, you'll get the last numbers. You will ask me, hey, from which number we have to do it, from which number we have to take the modulo. Simple, you get the last three digits, so take 1000. Okay, so take the modulo of number, that is modulo of number modulo 1000. Okay, simple, you'll get the last three digits. Now what is our next thought process? If you got this 786, for example, this is our last, let's suppose a number, then you take this first 100 position guy, you take this first 100 position guy. How do you get this first 100 position guy? Simple, divide this number, divide this number by 100, you'll get the 7, you'll get the 7. Once you get this 7, means 7 is stored somewhere. Yes, you are right, 7 is stored in this below 20. Okay, so the thought process is simple. Divide the number, divide the modulo number, divide the last 3-digit number by 100, to get the 100 position guy, Okay, simple. Now what is the thought process? 786, you got this 7, now you want this 86. 86 means last 2 digits. What is the thought process? Yes, take the modulo by 100. So again, to get tens and ones position, modulo nums by 100. Simple, modulo ones by 100, you will get this 86. Now check whether this nums is less than 20, nums is less than 100, or nums is less than, like, the else condition, which is greater than 100, If it is greater than 100, that is 786, for example, it is greater than 100, again call this. But in the call, you have to take this 100 position first. Okay, so for now we need just 86, which is less than 100, So what we will do is, if it is below 100, means take this number, again divided by 10, you will get this tens position index, and call tens of this nums divided by 10. Call this index, in the return store this index somewhere. So word equals to first this 100 guy, for this 100 we call this below 20 function. Okay, and we pass the nums divided by 100. Okay, now this plus, we will call this tens function. Okay, and this tens function, we will return this nums divided by 10. Okay, so now we will tell, now we'll ask me, okay, this 8 is done, now it is a time for 6. So from this 86, how will we get the 6? Yes, simple, again modulo nums by 10, simple, we'll get the 6. Okay, again check this condition. Now it is just 6. So in this word, again append plus, what we will call, yes, we just need 6, we'll call this below 20 function, and in this below 20 we will pass this nums by, no, there is no division here, because it is just a single element. We just want single element. So in the nums, it is, now in the nums 6 is stored. Just call below 20 and nums. You will simply get this 6, append the 6 in the word, and you are good to go. Do the steps for all this division. Now what is the next process? Thought process? After the new word is updated, check the index I, at which index I is positioned. If it is 1000, means you have to append 1000. If it is million, you have to append million. If it is million, you have to append million. So after new word is updated, check the ith index. In which function? Yes, in TMB function. Okay, so index in TMB function. Okay, and append the result of this TMB here. So what is the TMB function will return? It will return the position of that. It will return the value of that index of I. Okay, so plus TMB. Sorry, it's TMB and of I. Append this, and you also know that we are storing the previous word also. Somewhere. Okay, so again append what? Yes, the previous word. This is a simple thought process for this question. So if I write the formula for each and every updated word, so if it is word, then we will call some text function and we will pass nums. Modulo 1000 plus what is the next? Yes, TMB. Oh, sorry, my bad. It is TMB of I plus this word. This check function will return us one word. That this word is nothing but this word is this only that we are storing. Okay, this word is again updated with this word, and the process goes on until nums is greater than 0. Once the nums is less than 0, stop the process and return the answer. Simple. This is the simple thought process for this question. I hope you got this thought process. Yeah, it is somewhat tricky, but once you will do the dry run of this code, no, you will understand this question in much better way. Okay, so we'll write the pseudo code for this question. So we have one function. This function is carrying one number, that is int num. If this is first edge case, that if number equals to 0, just simply return 0. Simple, nothing There is no rocket science in this edge case. Then I told you we need some I pointer. We need some I pointer to traverse in TMB function. Initially it is zero. Initially it is zero. Now what we'll do is we also need one word which we have to return as an answer. Okay. So this is first initial word. We will assign it as empty word. Okay. Now what is next? We will call one function when until nums is greater than zero. Until this nums is greater than zero. Check what we need. What we need, for example, 111, 256, 789. We need this last element. So check if nums modulo 1000 is it. If it's not equal to zero, means we'll use some functions. We'll use some logic. But if it is equal to zero, for example, 2000, this is equals to zero. Modulo 1000 is equals to zero. Then simple. What we need to do is num equals to nums divide by this 1000 means you will get only two. And increment the I. Right? So if you divide by 2, you get I. Again, if you'll check this, yes, nums is greater than 0, no issues. Again, this function will check nums modulo 1000 is not equal to 0. No, it is not equal to 0. Now we will write our main logic. Okay, right. So main logic says we have to each time you have to update word. Okay. So I write the same formula that I have written it in our thought process. Yes. What is that formula? Right. Check will call one check function. We'll make one check function which will return the updated words. Okay. So check what we will pass. Yes, nums modulo 1000. We will pass this. Okay, plus tmb of I. We want the in which division that number is lying. Plus we return some empty string. This string is just to pass the test cases. Okay, so each time a new word will come, we need some gaps. Okay, for example, it is 1000. Okay, so there is one gap, one space gap. So for that reason, we are using this space. Okay, nothing much. Right. Plus the previous word that we have stored. Simple. Okay, and this loop goes on until this nums is greater than zero. Right. Now we will write our check function. The check function will take, yes, what it is taking an integer. Okay, so let's suppose we name it again it as nums. Okay, this is a check function check. If the number equals to 0, this is the first edge case. Okay, if number equals to 0, then simply return null. Our iteration is over. The check function will return null simply if it is equals to 0. If the number is less than 20, yes, just just rewind the video and check the thought process. If the number is less than 20, yes, what you need to do is you need to return which function. In which function we are storing 0 till 90? Yes, in below 20 function. In the below 20 function. Okay, just return the nums. Simple. If I have to write it as else if. Okay. So else if number is less than 100. If number is less than 100, divide the number. Yes. So for each time, if it is 768, divide the number into 3 parts. You want this number, and this is only 7. So what you will do is yes. So now it's else if number is less than 100. So for number which is less than 100, for example, we'll take 68. If number is less than 100 means 68. Again, divide this number into 2 parts. Again, divide this number into 2 parts. What you want? 60 and 8. 60 is stored in which function? Yes, it is stored in tens function. You will call, hey, tens. Take this 6 and return me the element which is present at 6. Okay, so tens, number divided by 10. Okay, number divided by 10. Again, you have to call this check function because it is recursion. What you will do is, yes, with some space, you will again call this check. Function. Now, which word you need? You just need 8. Yes, you just need which word you need? Yes, you need just 8. Which is last element. Last element means number modulo 10. You just need number modulo 10. Call this function again. It will give you number modulo 10. It will come here. Yes, 8 is less than 20. Call this function. Append the word. Simple. Okay. Right. So now if it is 768, means it is not less than 20. It is not less than 100. Yes, it is. It will come in our else function. Return. What you will return? You will call first below 20 function. Why? Because 768 means you just need the 7. So below 20 function, you will call this nums divide by 100 because you need this 7. If you divide by 100, you will get 7. Okay. Plus, I told you in the thought process, you have to append 100 manually. Okay. So 100 plus now which function you will call? You will call again this check function. You call this check function again for the 68. Okay. So 68 will be called in this else if because it is less than 100. So check nums modulo 100. Once this function is over, it will return us 768. This return call will go in this word, and this word is updated from first it was null. It was updated to this 768. Recursion will work, and our answer will get printed. Right. So this is a simple pseudocode for this question. I hope you got the pseudocode, and now we will check this code in Leetcode. Right. So now it's time to solve this question in Leetcode. Okay. So this is the 3 functions that we are calling that we have made right manually. That is below 20 function which stores 0 till 19th index. We have our tens function which will store from 0 till 90. We have this TMV function which will store ones position, thousands position, million position, and million position. Okay. So our main function starts from here. Number 2 word. Okay. So we have assigned an empty word. This word will return as our answer. This index I is to traverse in this TMV function. Yes, because we need the last three numbers. Then again again 3 digits, then again 3 digits. Okay, so this I will help us to traverse in this PNB function that we have seen in our thought process as well as in our pseudocode as well. Okay, so this is the first edge case. If nums equals to 0, just simply return 0. Just simply return 0. If the nums is greater than 0, means our main function will start, main logic will start from this. Okay, if the number modulo 1000, if it is equals to 0, then directly come here. Then directly come here to this nums. Divide, if you have 2000 divided by 1000, you get only 2. Increment the I. Again, this if will call, again this if will call 2 modulo 1000, it is not equals to 0. This word will call and this check function will call. Okay, so but for that, the I is already implemented, right? For example, if it is not 2000, then simply it will first come in this check, in this if check. Okay, this check function will call in this nums modulo 1000. This nums modulo 1000 means it will get our 768. Recall our pseudocode. It will return our 768. Yes, this 768 will be passed as the argument in this num in this function check. Okay, it will first check this 768 equals to 0. No, it is not equals to 0. Is it less than 20? No, it is not less than 20. Is it less than 100? No, it is not less than 100. It will come in this check. It will come in this check. In this check, it is returning first what? Yes, below 20 function is running. It will take this number divided by 1000, number divided by 100. 768 divided by 100. How much? Yes, only 7. Only 7. Again, this check function. Okay, what will this below 20 function will return? 7, because at index 7, 7 is stored. Simple. Okay. Then we will manually appending this 100. Then again, we will call this check function for this 768. 7 part is over. 68 is left. We need this 68. Again, this check will call with argument 68. 68 equals to 0? No. 68 is less than 20? No. 68 is less than 100. Yes, 68 is less than 100. Our tens function will be called. Yes. In this tens function, what we will return? 6th index. In the tens function, 6th index will return me 60. 60. Okay, so 60 is written over here. Plus with some gap, we'll again check 768. 7 part is over. 6 part is over. Now 8 part is left. 8 part is left. Again, check function will be called with argument 8. 8 is equals to 0. No, 8 is less than 20. Yes, it is less than 20. We will call this below 20 function with argument 8. With argument 8, 8 will be written. 8 will be written. In this return call, it will be 8 is written in this call. This return call will go again here. Okay, because it is recursion, it will go upwards. Okay, this check function will again return over here. So we'll get this 700. This check has written me 68. This check has written me 68, and this return call will again comes back to this word. It will again comes back to this word. Right now our I is 0. Right now our I is 0. So in our TMUFI it is null. In our TMUFI it is null. Plus our previous word was empty. Now what is our new word? 768. And again comes here. 768 means 111, 256, 768. So 768 part is over. Now 111, 256 is left. Again divide this number by 100. So 768 is removed. 111, 256 is left. Now this process will run until this number is greater than 0. Once the number is less than 0, we'll simply return the word. You will ask me, hey, why have you written this trim over here? So whenever you will return this, for example, so whenever you will return this, for example, it is returning 768 EIGHT, and you will get this extra space. You will get this extra space. So to remove this extra space, we need the stream. The stream is basically in Java. It will remove the extra spaces from the back. Okay, extra white spaces. So for this reason only, I have used the stream function. Right. So this is the code for this question. We will test this code in our test cases. I hope this will work. Okay, right. Oh, I have to change this to Java. Okay. So now we will check this function. We'll check this function. I hope. Yes, all test cases are passing perfectly fine. We will submit this code. Perfect. The code has been successfully submitted. I hope you guys understood the concept of mathematics and this modulo, right? So this is it for this video. Thank you. Have a nice day.